Alright, so the timer is done. So let's start talking about physics then. Okay, so for this semester, the first topic we're going to talk about is thermodynamics. So this word, some of you might have heard before. What does it mean? Well, it's the joining of two words, thermo and then dynamics. Dynamic is what you learned already from first semester, which means something that involves the motion. Okay, thermo is something that related to like thermal temperature, energy, or that stuff. So thermodynamics essentially is the study of the dynamics of energy. So how energy flow, how temperature affect all that stuff. All right. One important concept that we need to talk about obviously is called temperature. And this is something that you are very familiar with during this lockdown period, of course. Because if you need to go to somewhere, there's someone, taking the temperature of yourself to see whether you have a fever or not. But if you don't have a fever, then you are allowed to get into, let's say, the bank or something, right? So what is temperature? This is something that we are used to, but to explain it, precisely in physics, actually it's not that simple. So we're gonna do some kind of like a thought experiment. Well, not really a thought experiment, but kind of something that we think about if we talk about temperature. And in order to do that, we need to talk about what we call the zeroth law. Of thermodynamics. So what is this? This law actually defines what a temperature is. Okay, well, not directly, but it's related to temperature. So what we have here is, let's say we have an object. Let's say object A. Something. It might be a block of aluminum or any material that you want. And then you have another block, which is called block B. And what we do is we bring these two objects into what we call a thermal contact. Right? So a thermal contact means you allow energy to flow from one object to the other object. So you bring A and B together like this, right? And it doesn't really have to be like this. It can be the case where you put some ice in a cup of water, then ice and water will be in what we call thermal contact, right? So if you think about some situation like this, right? You have some water and then you put some ice in here, right? So ice and water will be in thermal contact in this case, right? So ice and water are in thermal contact. In thermal contact means energy can flow from one object to the other object. So in this case, we have A and B. Okay, so in principle, you can have the flow of energy from A to B or from B to A. Okay, it can happen in both ways. And the flow of energy, we're going to use the letter Q. Right. So in this case, we can say it's Q from B to A. Right. Use this way of writing. And up there, we can write Q from A to B like this. Okay. So Q is the flow of energy. Sometimes we call this heat. And this is the definition of heat if you want. Heat is the flow of energy. Okay, so going back to this situation, most of the time Q from B to A and Q from A to B will happen at the same time. Okay, so we need to write down the net flow of energy. So we can write Q net. Okay, so if you want to write Q net, then you need to kind of decide what point of view you are talking about. So if you're gonna talk about A in particular, right? So we're gonna define the sign such that if it's positive, then energy is flowing into A. Okay, so in this case, it should be clear that we have to write B into A because that's the energy that flow into A. Let's say Q net for object A, and then minus Q from A to B. Right. So why the minus sign? So the minus sign because this part of heat flows away from object A. Okay. So object A lose energy because of this term, and object A gain energy because of this term. Okay, so the sign is very important. So similarly, we can write Q net for B. So from the point of view of B, right, then the sign will be reversed. Okay, Q from B to A, from the point of view of B, it's flowing away. So in this case, you're gonna have Q A to B. This is positive because it's flowing into B, and then minus Q B to A, which is just minus QA net. Okay, something like this. So this part is quite important. Q net of B equal to minus Q net of A. So what does this mean? This means that all the energy that flow away from B must go into A and nowhere else. Otherwise, you lose energy without any good reason. Okay, so this minus sign gonna kind of indicate that the total energy flow must be 0. So if I combine this and this together, right, from QB net plus QA net must be equal to 0. So that means our system, which consists of A and B, okay, so A and B is a closed system. That means it's isolated from other things. Okay, so everything that's happening in terms of the flow of energy happens within the system. So all the energy coming out from A must go into B, and then vice versa have to be true. Okay, so what is the zeroth law of thermodynamics? Zeroth law of thermodynamics is that it talks about in equilibrium. So under what we call thermal equilibrium, under thermal equilibrium, then QA net equal to 0 and QB net also equal to 0. Okay, and if this is the case, then this equation is automatically satisfied. Alright, so this equation QA net plus QB net has to be 0. It doesn't mean that each one has to be 0. Okay, so this one can be some positive number, this one can be some negative number, and they add up equal to 0. That's fine. But under thermal equilibrium, this is this is a strict, it's a more strict condition. It means that QA net equal to 0 and QB net equal to 0. Okay, so what does this mean? This means no heat flow into or out from either A or B. Okay, so net heat flow from A and B coming out, going in, this all 0. This is what we call thermal equilibrium. Alright, so then when this is the case, we say that A and B are at the same temperature. And then temperature, we're going to use big T to indicate this quantity. Okay, so A and B are at the same temperature is exactly the same as saying that they are in thermal equilibrium. And what does being in a thermal equilibrium means? It means that if you put A and B in thermal contact like this, there's no heat flow between them. There's no net heat flow between them. What happens if you are not in a thermal equilibrium? Well, for example, you have A, and then you have temperature of the object A, let's call it TA, and then you have the object B, and then you have TB. So let's assume that for whatever reason, TB is larger than TA. Okay, so temperature are not the same, so they are not in equilibrium. They are not in thermal equilibrium since the temperature are not the same. In this case, there's going to be a net heat flow. So there will be some heat flow this way. So this means QB net is some negative number. Let's, for the sake of argument, say it's minus 100 joules. Okay, so minus sign means that the heat flow out from B. And since QB and QA add together must be equal to 0, so QA net is obviously 100 joules. Okay, so heat gonna flow from hot object to cold object, and hot and cold are the notion that we use to describe the temperature of the object. right? So if the temperature of B is larger than A, then we say TB is hotter, not TB, TB is hotter than A, right? So this is another way of saying that TB is larger than TA. Okay, so in this way, it's kind of like a very indirect way of saying what the temperature is. So it's the thing that we can use to determine the direction of the flow of the object. Okay, and so how do we measure temperature then? Well, you need to have some property of the material that responds to the what we call temperature. And one easy thing to use is the expansion property of material. So one easy thing is to take gas. So let's say we have a cube. Oh, well, actually better if we use like a cylinder that contains kind of gas, right? So this cylinder has what we call a piston that can move around. So this is what we call a gas container. Okay, and then the gas is in here. So it's kind of like a can that can change the volume by moving up or down this piston. So piston can move up or down. Okay, so that means the volume of the gas, which is this part, can also change by moving the piston. Okay, so this gas is maybe, like oxygen gas or whatever. It doesn't really matter, but the important thing here is that if we heat up the gas, then it will expand, right? So the gas container will expand. Well, let's see. I just draw it badly, then you just have to bear with me. So this one becomes larger when you heat up, right? So V becomes V prime. So volume expand. I should say volume of the gas expands when T increases. Okay, so well, I should say that, okay, keeping the pressure constant, whatever, but let's just ignore that part. We're gonna come back to that later. But under normal circumstance, this is something that you are used to in your daily life, right? If you have like a balloon and then you heat up the balloon, it's gonna expand, the volume gonna increase. Okay, so this volume here, so it's clear that the volume here depends on the temperature, right? So in a sense, we can use this gas in a container as a measuring device that measure the temperature. Okay, so if V depends on T, volume depends on temperature, then we can use this gas container as what we call a thermometer. Which is essentially anything that change according to the temperature. Okay, so this is what we can use as a thermometer. So we can look at how the gas expands, right? If you have the gas which expand larger than in other case, then you can say that the temperature is higher, right? So V depends on T. We can use this as a thermometer. Okay, so now we have a thermometer, then we can use this to measure anything that's happening. For example, with some better engineering, you might be able to use this principle and then make a easy to use thermometer, right? And then you can use that as a thermometer for anything, right? So with very good engineering, you can make it to look like this. Very familiar to everyone, right? So, and then you have a scale, right? So you can have a generic thermometer where the thing that expands might not be the gas, right? It might be some other liquid, but the principle is the same, right? It's something that changes when the temperature changes. So we have a thermometer, then we need to kind of agree upon like how we're gonna call like the number of the thermometer. Like 0, what does it mean, 0? Right, 0 in temperature, what we have to agree with that. So the easiest thing that we use is to define 0 degrees Celsius. Okay, just keep in mind that this is in a sense very arbitrary, right? It's just that the guy named Celsius, which was born like 300 years before us, decide that he's gonna call this 0 degrees Celsius. Well, if you were born earlier than that and then you happen to know a lot of physics, then you can define your own temperature scale, right? But it's too late, so we're gonna have to stick with this. So 0 degrees Celsius is defined to be the temperature T in which water freezes, which is the same temperature as ice melts. Okay, we just call this one 0 degrees. Okay, and water is one of the most like ubiquitous matter, so that kind of makes sense. And then 100 degrees Celsius is defined to be T in which water, well that boils, or vapor condense. Right, so one interesting thing we're gonna talk about this a little bit later is that if you take water in Thailand and then you take water in like Switzerland and then you take water in the US, they will freeze at the same temperature, okay, provided the water that you get does not contain any strange stuff like like mineral water or something like that. Let's just say it's pure water, but it's pure water that you get from somewhere else, right? But no matter what, they all freeze at the same temperature, and also they boil at the same temperature. So it's a very good thing to use as the temperature standard here. Okay, so 0 degrees is when water freezes, and 100 is when water boils, right? And then from these two, we just say, okay, let's just divide this into 100, 100 degrees. So that's how people got 0 degrees Celsius to 100 degrees Celsius. It's from this kind of, seemingly arbitrary definition, but it's something that we use. Okay. The only country that doesn't use this is the US, I think, which use Fahrenheit. It's defined in the same way, but instead of using water, a person named Fahrenheit used some other mineral oil, I think, that freezes at different temperature and then boils at different temperature. Okay, so that's 0 degrees Fahrenheit and 100 degrees Fahrenheit is different from Celsius, but we don't really use that here, I think. So you don't really need to remember that. Okay. But if you are used to this degree Celsius, then you know that sometimes actually not that hard to find a situation that you need to go to negative temperature. You need to go to minus 10 or minus 15. Like if you go into the freezer in your refrigerator, so a freezer in a fridge, that's probably going to be at minus 15 or something degrees Celsius. Right, so, and then some of you might have been to a very cold country, then the temperature that you have during the day can be also minus 10, minus 20 degrees Celsius. That's totally possible. And, it might be a little bit strange since you are here in Bangkok, right? But that's possible. So the question is that, how low can it go? If 0 degrees Celsius is when water freezes and it can go to negative, can it go to negative 200 degrees Celsius? Can it go to negative 300 degrees Celsius? Is there a limit on how low you can go in terms of the temperature? The answer is actually yes. Okay, so how low in terms of temperature can we go? So in order to do this, it's better to go back to our kind of primitive thermometer here, right? So remember that we use the volume of the gas as a thermometer, right? So the larger the gas is, the higher the temperature, right? So we can do an experiment. We can plot the temperature and volume of the gas. So let's say we have temperature in terms of degree Celsius and then volume in a standard unit, which is meter cube, something like this. And then you measure how the volume changes when you change the temperature of the gas container, right? So what you're gonna see is that it's gonna increase when the temperature rises, maybe something like this. Okay, at 0 degrees Celsius, it's cold, but it's not cold enough. What do you mean by cold enough? Well, there's still some volume at 0 degrees Celsius. Okay, so that means you can go lower. If you can go lower, then you're gonna measure the volume lower at lower temperature, right? So you're gonna do the experiment. You're gonna lower the temperature until the volume of the gas actually hits 0 here. This point. It might not be possible to do this in real life because going to low temperature requires a lot of hard work, right? So you might need to do the experiment. You get a few data points and then do what we call extrapolation to see if in principle you can measure until the volume is 0, what would that temperature gonna be? Okay, and you can choose different kind of gas, and interestingly they all go to 0 at the same temperature, right? So if you have another gas, different type of gas, maybe this one you use oxygen and then you use nitrogen, something like this, you're gonna have another curve that looks something like this. But if you do the same thing, you do the extrapolation, this curve will also intersect at the same point here. Okay, so no matter what kind of gas you use, you do the experiment and you extrapolate. Well, this one, my line is not really straight, but you get the idea, right? They're all gonna intersect at this point, right? So what is this point? That point is when volume equal to 0 of the gas. So that means you cannot go any lower than this, right? So the volume is already 0. You cannot go to negative volume. I think I don't know what that even means, right? So this is what we call the absolute zero temperature. And this is the lowest temperature that we can, in principle, get anywhere in the universe. Okay, no matter how much more expensive you pay for your freezer, it's not gonna go lower than this. Okay, so where is this exactly? Well, this one happens at T0 happens at minus 273.15 degrees Celsius. So it's very, very cold. It's 273 degrees below freezing point for water. Okay, and then you cannot go lower than this. Because of this, in physics, most of the time, we're gonna use the temperature scale, which is called Kelvin temperature scale. So T0 will be defined to be 0 Kelvin, like this. Okay. So we're gonna use Kelvin as our unit for temperature, and at 0 Kelvin, everything is 0. Volume is 0, energy is 0. Okay, so you cannot go lower than this. To change from Celsius to Kelvin, you just need to add or subtract this number. So we have a really simple formula if you want to remember this, right? So T in Kelvin equal to T in degrees Celsius plus 273.15, like this. And one thing I want to kind of like tell you, just so you know, is that when we talk about Celsius, we say degrees Celsius. When we talk about Fahrenheit, we say it's degrees Fahrenheit. But if we talk about Kelvin, we just say Kelvin, there's no degrees in it. Okay, so it doesn't, or it's not strictly speaking true, correct. If you say degrees Kelvin, right, just say, okay, the temperature is 10 Kelvin, 300 Kelvin, or 400 Kelvin, like that. Okay, so that's the thing that we're gonna use. Okay, and so 273 is just the shift in the temperature scale, like where do you call 0. For Kelvin, 0 is really 0, is the absolute 0. For degrees Celsius is when water freezes. Okay, but sometimes we're gonna talk about the change in the temperature. Okay, so the change in temperature is the same for Kelvin and degrees Celsius. Okay, change in the temperature means is delta T. Okay, delta T is final temperature minus initial temperature, and it's the same no matter which unit you use for degrees Celsius and for Kelvin. And I'm writing this because when you do the problem, sometimes you need the absolute temperature. Sometimes you only need the change in the temperature. Okay, so the change in the temperature, they are the same. But for the absolute one, you need this number to shift it. Okay, just a quick kind of like note on, well, how like different number in Kelvin, what does it really means. So if you can, draw a quick line to indicate the temperature, and water freezes at 0 degrees Celsius. So that means in Kelvin, that's going to be exactly 273.15 Kelvin, right? So if I indicate that line here, 273 roughly Kelvin, that's when water freezes right at this temperature. And to go lower, then you need something which is colder. And the easiest thing you can find is what we call liquid nitrogen. Well, that's probably not the easiest. I think during this lockdown, most of you order food from, like Grab or Line Man or something like that. And sometimes you order ice cream, right? And ice cream comes with dry ice. Okay, so dry ice is, I don't remember exactly the number. I think maybe about 220 something Kelvin. I need to check that again. Okay, so that's dry ice. I might be wrong here. So actually, let me quickly Google that. So dry ice is actually a solid form of carbon dioxide. So that's the gas that you can make it like an ice cube, but it's really cold. So it's actually minus 78 degrees Celsius, so it's roughly about 200 Kelvin. That's dry ice. Okay, so it's cold enough to keep your ice cream from melting. And then if you can get what we call like liquid helium, that's roughly about 4 Kelvin. Liquid helium. That's what people use when they do experiment with, really cold stuff in the laboratory. So you can buy liquid helium, which is actually quite expensive, but it can get you to a very cold temperature. Okay, and then of course you can go to 0 Kelvin. That's the absolute lowest temperature that you can go. You can go to higher, right? So let's say you can go to, you can fly to the sun, right? That's about 10 to the 7 Kelvin. That's inside the sun. And then you can actually make even higher temperature by making a bomb. So this is kind of like atomic bomb. So during the first millisecond of the bomb detonating, is actually get very, very hot, 10 to the 8 Kelvin. Okay, so there's no limit on how high the temperature can go. Okay, because maybe if you put all the energy of the universe into somewhere, then maybe there's a limit. But in the lowest temperature, you cannot go below 0 Kelvin. Okay, because that's when everything freezes. Okay, so the next thing we're going to talk about is to talk about one kind of property of material that depends on temperature. It's kind of like the expansion of what we talk about here, which is the volume of the gas expand when temperature increases. But we're going to be a little bit more specific and then talk not just for gas but for any material. And this is the topic of thermal expansion. So if you take, a piece of, wire that made from metal, let's say it's a wire which is long. So why do we have to talk about the wire? So that we don't need to worry about the other dimension, right? So we can talk about just the length of the material here. So L0 is the length at any temperature that you want. Right? Let's say room temperature, like about 25 degrees Celsius. So that's L0. Okay. So if you heat up this object, and how you exactly do that, it's up to you. So you can put this in boiling water, or you can just use a flame torch to heat this thing up. When you heat up, most of the material will expand. Okay, that's a quick question. For Kelvin, is it liquid helium or solid helium? It's liquid helium. Okay. Helium is a very strange material that most of the time it will just stay as liquid. Even if you go to extremely, extremely low temperature, helium will not be solid. Okay, so it will stay liquid all the time. So liquid helium is at 4 Kelvin. Okay, so not solid. But for dry ice, that's solid carbon dioxide. Okay, it's a very strange kind of property of different material. All right, let's get back to this. So when you heat up the temperature, so I should say that this is kind of temperature. At some temperature, let's say for the sake of argument, this is at 300 Kelvin. And the length is L0. So when you heat this up, most of the material will expand. Expand means it's going to get longer. So let's say it's get longer by this much. Okay. So that shaded area, that's the change in the length. Okay. So delta L is the change in length of this material. So the total length of this thing is L0 plus delta L. This is the new length of this material. Okay, it's L plus delta L. And we have a formula that relates delta L to other quantities. And this one is probably the kind of the one that you can remember. Is good to know, is the thermal expansion equation. So delta L is some number alpha, we're going to come back to this, times L0 and then times the change in the temperature. Okay, so we have three variables, this thing, alpha, L0 and delta T. So let's talk about the easiest one first, which is L0. This is just the length before you change the temperature. Okay, so this is the length L before changing T. And delta T is the change in the temperature, change in T. So it's T final minus T initial, right? So if we want to be very specific, then all the T that belongs to the initial temperature, I have to put in subscript I. Sorry, I don't need it here. Right. So L0 is the length at Ti, which we say is 300 Kelvin. Okay. So before we talk about alpha, there's another thing I want to point out for delta T here. So delta T can be either positive or negative. So positive delta T, positive means you heat it up because the final temperature is higher. Delta T is negative when you cool down. Right, so that's the sign of this delta T thing. So every other parameter are positive. Length is positive, obviously. And alpha, well, some of the thing has alpha negative, but we are not going to talk about that. But so let's assume that alpha is also positive. So that means if delta t is positive, delta L will also be positive. Delta L positive means the length increases. Delta t negative gives you delta L negative, so that means it's gonna shrink, right? So the length gonna decrease, right? So you heat up, it expands. You cool down, it shrinks, and that's kind of like 99% of the material that you're gonna encounter in life, unless you have a really strange job. Okay, what about alpha here? Alpha here is what we call, so the full name is a little bit long. It's called the linear thermal expansion coefficient. Okay, it's very long. It's called linear because it describes the increase in the length, which is one-dimensional thing. It doesn't talk about the increase in the width of the wire because the width is really small for this particular one. So that's what we call linear. Later on, we're going to talk about, the area expansion, the volume expansion, which is not the increase in the length, but the increase in the area or the volume, right? So in that case, we're going to have not linear thermal expansion coefficient, but something else. Yeah, but for most of the metal or any solid stuff, we're going to talk about linear. And thermal expansion coefficient is just self-describe what it means, right? So the important thing of this is that alpha is a property of material, right? So you might be wondering, okay, this equation looks good, but this applies to different kind of material. Where does different kind of material enter in this formula? It enters in this alpha. So different material will have different alpha. Okay, so let's take a look at one table here. So this is the table that I got from one of the textbook. Okay. I actually saw one quick question about which book edition are we using. It doesn't matter, like I said earlier. We are not following strictly from one particular textbook. So any textbook is fine. I mean, you can see that you take 10 textbooks about thermal expansion, they're gonna explain roughly the same in every textbook. Okay, so you don't need to go out and then buy specific edition. Is any edition is fine, or any other textbook is fine. Okay, and for the homework, I gonna post the problem anyway, so don't worry about that. All right, this is the linear expansion coefficient. The unit is 1 over degree Celsius or 1 over Kelvin. It's the same because we talk about the change in the temperature. And the change in the temperature for Kelvin and degree Celsius, they are the same. Okay, so allow me to go back a little bit here. So if we look at this formula and then we analyze the unit. Okay, so we write down the unit. To write down the unit, I'm going to use this notation, which is a bracket. So I'm going to say bracket M. So that means the unit of delta L I use is meter. And then the unit for alpha, if you don't know. And then the unit for L0 is also meter, right, because it's also length. And then the unit for delta T is Kelvin or degree Celsius. Okay, it's the same. So when you cancel out the unit, you get the unit for alpha is unit of Kelvin to the minus 1. Okay, or degree Celsius to the minus 1. So it's per degree Celsius or per Kelvin. So alpha tells you the percentage increase. Another way of looking at this is to put delta L over L0 on the other side, equal to alpha times delta T, right? So what is this? This is the increase or the decrease of the length compared to the original length. So it's a percentage, right? It's a percentage increase or decrease. So this one might be also easier to remember, right? So if we go back to this table, so you can see that alpha is usually pretty small, okay? So 24 times 10 to the minus 6, that's a very small number, okay? So how small it is? Well, let's just take a quick number here. So let's say you have a piece of aluminum that is, 1 foot long. How long is 1 foot? That's 30 centimeters, right? Like this. And let's say it's aluminum, okay? And let's ask kind of like a stupid question. Let's say you have a chopstick that is made from aluminum, right? And then you stick this chopstick into your noodle soup, okay? And then you ask, okay, how long my chopstick gonna be after I put this chopstick in my noodle soup? So before you put in, let's say T initial is roughly about 300 Kelvin. That's about 20 or 30 something degrees Celsius. Okay, and let's say noodle soup is like 20 degrees Celsius hotter. So let's say TF is 320 Kelvin. Okay, so what will be the length of this chopstick gonna be? And actually, 1 foot chopstick is kind of long, right? No, maybe you can buy one, but that's not usually what we use. But anyway, let's just calculate this. So let's calculate delta L, which is alpha times L0 times delta T, okay? And alpha, we're gonna use this number here, which is 24 times 10 to the minus 6, 1 over degree Celsius, times the initial length, which is 0.3 meter, times the change in the temperature, which is TF minus TI. So it's just 20, right? And like this is the third time that I've said this. The delta T in degrees Celsius and Kelvin is the same. So I can use like this, okay? And then you just calculate this. So I'm going to calculate this times 0.3 times 20. And then what you get is 1.44 times 10 to the minus 4 meter. Right. How small is this? Well, it's 0.14 millimeter. Right. So you don't even see it. Right. You don't feel that it's actually getting longer, this chopstick, because thermal expansion coefficient for regular metal is just so small that most of the time you don't really see this effect. But if you talk about a really large object, a really long object like a section in a highway, right? That can be 1 kilometer long, right? Then delta L is gonna be also scaled up, 1,000 times, and that becomes really, really observable, right? And that's gonna be the important thing when people are, designing the railroad or a concrete section on the highway or something like that. Okay. One particular interesting thing is this one, which is called Invar. So Invar is a very low expansion metal. It's an alloy. Alloy means it's a mixture of different kind of metal. So it's a nickel and iron alloy. So it happened to be a very low thermal expansion coefficient material. It's quite expensive, but if you have application where you don't really want to change the length that much, then this is the one to go. Okay, So if you want, maybe if you want to own a pair of chopstick that doesn't expand when you put it in like noodle soup, then you might need to make one from Inwa. Okay. For some material, most of the time it's liquid, right? So we can't really talk about the linear expansion because most of the time we're going to talk about the increase in the volume, right? And I'm going to go back here because there's some space here. So for liquid, we talk about volume expansion. Okay, we talk about volume expansion. So the idea is the same. It's like you have some kind of liquid in a container, and initially it has some volume V0, and then when you heat up this same thing, gonna expand and get higher volume like this, right? So sorry for the bad drawing. So in the same way, the new volume is the old volume plus delta V. Okay, so delta V is the change in the volume, right? So we can have kind of like an analogous to the formula that we have here. So instead of delta L, we're going to talk about delta V. So in this case, delta V is what we call beta V0 and then delta T. So everything is the same except for this one. So this one is no longer called linear expansion coefficient. It's called the volume expansion coefficient. Okay, so it's volume obviously because for liquid, volume is a lot easier to deal with compared to the length. Okay, so you're gonna have another table here which talks about the volume expansion coefficient, and most of these are either liquid or gas, right? So it's a thing that is really hard to make it into a straight line, like alcohol, which you cannot buy for a few weeks already. So hopefully you're all doing fine with that. Acetone, okay. Glycerin is also kind of liquid. Mercury is metal, but is one of very few metal which is liquid in room temperature. So for mercury, we have to talk about volume expansion coefficient, okay, not the linear one. If you want to freeze mercury, you have to go to, I think, minus 200 something degrees Celsius. And then gasoline obviously is liquid. And then air and helium, these are gas. Okay, so for gas, you also need to talk about the volume expansion coefficient. Okay. It can be shown that if you know the linear expansion coefficient, you can calculate the volume expansion coefficient or the area coefficient for that material. It might be not quite appropriate for this guy because these are liquid anyway. But you can ask this question like you have a sheet of aluminum, not a rod, not a wire, but a sheet of aluminum, right? Which has the initial area of A0, and then you heat it up, this thing will expand, so the area will increase. Right. So A is A0 plus delta A. Right. So we can talk about the area expansion coefficient, like A, delta A is some kind of factor here, which I don't know what normally people use. No, most of the time people don't talk about this, but I'll just write gamma just for the sake of writing down, times A0 times delta T, right? So this is the change in the area. So this one is the area expansion coefficient. Okay, and it can be shown that gamma is actually twice alpha, which is the linear expansion coefficient. Right? So it's quite interesting to see like how you get about this. Okay, so it's just twice the linear expansion. So if you continue for this aluminum piece, right, you take aluminum, which is a cube, which has the initial volume of V0, and then you heat it up, it becomes a bigger volume, right? And then delta V is the same as what we had earlier, delta T. It can be shown that beta here is just 3 times alpha for the material that you know what alpha is. Okay, so in principle, you don't need another table for volume expansion for anything in this table because it's just multiplying this number by 2 or by 3. Okay, so for metal, most of the time we just talk about the linear coefficient. And for things which is liquid or gas, then we just talk about the volume expansion coefficients. And that's going to be enough for us to explain anything. Okay, so I think I'm going to stop here for today. So unless you have any question, then I will see you again on Wednesday then. All right, so thank you for staying with me and take care. I will see you in 2 days.